Hello, this is Coach Dorf again. We're going to look at a problem from section 4.5 that's similar to the homework, but not quite the same. In these problems, we're supposed to sketch the graph of a function to reveal all the important aspects of it. In this case, we're looking at f of x equals x minus 5/3 x to the 3/5 power. So the first thing I would do is look at what is the domain of this, domain of f. Well, I have restrictions on f if there's a 0 in the denominator, if there is a negative number under the square root or an even root, or if I have a log of a term and inside of parentheses, whatever's inside that parentheses cannot be 0 or negative. So I look at this, is there a 0 in the denominator? No, there's no denominator, so there's no restriction that way. Is there a square root or an even root? It may look like it at first, but there's not. We have x to the 3/5 here. That's an odd root, but not an even root. An even root would be something like x to the 3/2 or x to the 3/4. But we have x to the 3/5. The 5 is an odd number, so it's an odd root. So there is no restriction there, and there's no log function. So the domain then is all real numbers, or negative infinity to infinity. Asymptotes. Are there any asymptotes in this problem? Well, I could have a vertical asymptote. And a vertical asymptote would occur if there were 0 in the denominator. Okay, but we said we have no denominator, so there is no vertical asymptote. We'd have a horizontal asymptote if I took the limit as x goes to infinity of f of x, and that if that equaled some finite number. Okay, but in this case, when I look at this function here, and I take that limit there, that's going to equal infinity. And likewise, if I do x going to negative infinity of x minus 5/3 x to the 3/5, that's going to equal negative infinity. So there are no horizontal asymptotes. All right, the next thing I'm going to look at are intervals of increasing and decreasing. To do that, I'm going to find the critical numbers. So the critical numbers are when the derivative equals 0. So I'm going to take my function. Its derivative is going to be 1 minus x to the negative 2/3. Remember, when I take the derivative of 5/3 x to the 3/5, I bring the 3/5 out front. That cancels out with the 5/3. And then I have x to the 3/5 minus 1, which would give me x to the negative 2/3. I can rewrite that as 1 minus 1 over x to the 2/5. And getting a common denominator now, I have x to the 2/5 minus 1 all over x to the 2/5. So a critical number occurs when the derivative equals 0 and the derivative does not exist. So in this case, f prime of x equals 0, that's going to imply then that x to the 2/5 minus 1 equals 0, right? Which is going to mean that x to the 2/5 equals 1, which is going to give me then that x equals plus or minus 1. Now notice I'm going to get a minus 1 because if I take negative 1 to the 2/5 power, then that means I square it. So negative 1 squared is positive 1, and I take the 5th root of that, I still get 1. So those, both a positive 1 and a negative 1 are important here. And the derivative does not exist at x equals 0 because You have x to the 2/3 in the denominator of f prime. Now, an important point here, if 0 were not in the original domain, then x equals 0 would not be a critical number. It's only a critical number if it is in the domain, the original domain, and f prime does not exist. Let me emphasize that by writing this here. F prime does not exist at x, okay, where x is in the original domain. Common mistake that students make is to say that a place where the derivative does not exist is a critical number, even when that point is not in the domain. And that's not the case. Okay, I can then use these critical numbers to find the intervals of increasing and decreasing. So to do that, I'm going to make a set of intervals. I'm going to make -infinity to -1, -1 to 0, 0 to 1, and 1 to infinity. The points that make up these intervals come from the critical numbers. And I'm going to look at the value of the derivative at these critical numbers. So one way to do that is to use some different colors here. So I'll use green first. So on -infinity to -1, I'm going to take a number inside that interval. I'm going to look at -2. So this is going to give me 1 minus 1 over -2 to the 2/5. Well, what is -2 to the 2/5? Note, -2 to the 2/5, all right, that equals -2 squared all to the 1/5, which is 4 to the 1/5, which is about 1.3. All right, so when I put that in here, then into my original equation here, I'm going to get something that is larger than 0, because 1 over 1.3 is less than 1, so 1 minus something less than 1 is going to be positive. So this is going to be positive, so it's increasing. If I do the same thing on the interval from -1 to 0, I'm going to look at the derivative. I'll take a -1/2 here. So this is going to equal 1 minus 1 over -1/2 to the 2/5. And what is -1/2 to the 2/5? All right, so that's going to be the same thing as -1/2 squared all to the 1/5 power, which will be 1/4 to the 1/5 power, which is approximately 0.76. So now if I plug that back into the original derivative part I had here, I've got 1 minus 1 over something that's less than 1. So I'm going to have 1 minus something that's larger than 1, and so that's going to be negative. All right, so this is going to then be negative, and it's going to be decreasing. And I can do this for other numbers, for the other numbers, but in this case, this is going to be between 0 and 1, it's going to be negative. It'll be exactly like the purple case, except I have a negative number in there, but that negative goes away. And then for the last one, it's going to be positive, and it'll be increasing, just like it was for the interval -infinity to -1. The only difference is I have a negative sign there, but it goes away when I square things. All right. So the next part we want to look at is we did intervals of increasing Now we're going to do intervals of concavity of concave up and concave down. So to do this one, I look at the second derivative. So the first derivative was 1 minus x to the negative 2/3. The derivative of that would be negative times negative 2/5 x to the negative. Now I'm going to go ahead and subtract 1 from negative 2/5, and I get negative 7/5. So that's going to equal 2/5 x to the negative 7/5, which I can write as 2 over 5 x to the 7/5. Okay, when is that equal to 0 or not defined? That's going to happen when x equals 0. So I just have two intervals to look at for concavity: infinity to 0 and 0 to infinity. And I'm going to look at the second derivative of that. Again, when I have my derivative function here, 2 over 5 x to the 7/5, I can never get 0 in the numerator because I have a 2 there, but in the denominator I can get 0 when x is equal to 0. That's why we have x equals 0 as a point to look at. All right, now I just go ahead and look at this. When I put in a number in the first interval from negative infinity to 0, so let's say I just look at the second derivative at negative 1, I'm going to get 2 over 5, negative 1 to the 7/5. I take negative 1 to the 7/5. That means I take negative 1 to the 7th power. That's negative 1. Now I take it to the 1/5 power. I still get negative 1. And this is going to equal 2 over 5 times negative 1, or negative 2/5. So this is negative. So we have negative, negative, frowny face. So it's concave down. All right, if I do the same thing for the second derivative at 1, I'm going to get 2 over 5, 1 to the 7/5, and that's going to be greater than 0. So this is positive, 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 and it's going to be concave up. All right, let's see, anything else I want to mention on this function? Oh, yes, inflection points. We have an inflection point here. Well, inflection points are when it goes from concave up to concave down, or concave down to concave up. All right, at x equals 0, f goes from concave down to concave up. So that implies there's an inflection point at x equals 0. And the last thing I'm going to mention is symmetry. My original function again was x minus 5/3 x to the 3/5. It's an odd function if I put in negative x in for f into x, and when I do that, I'm going to get negative x here minus 5/3 negative x to the 3/5. So that's going to equal negative x minus 5/3. When I do negative x to the 3/5, that's going to be negative x to the 3/5. That negative can come out, and so I get negative x plus 5/3 x to the 3/5. That negative can come out because I'm doing negative x cubed, which would be negative x times negative x times negative x. So I still have a negative sign. And then I take the fifth root of it, and when I take an odd root of a negative sign, I still get a negative. All right, if I factor out a negative, I have negative parentheses x minus 5/3 x to the 3/5. And so that's the negative of f of x. And so it's an odd function because f of negative x equals negative f of x. And that means the graph is rotated about the origin. So let's use this information now to sketch the graph. So my significant points, and these aren't terms that are used in the books, but this is what I like to remember if I'm going to sketch it, are where I have points where the interval can change from increasing to decreasing, or concave up and concave down. And those points were x equals -1, x equals 0, and x equals 1. And I want to look at what the f value is, the value of the function at these points. When f is -1, I'm going to, let me just put it down here. F of -1 is going to be -1 minus 5/3 -1 to the 3/5 power. So that's -1 minus 5/3. Now, when I take -1 to the 3/5 power, that's a negative sign. That's to the 3/5 power. That's the same thing as just a -1. Okay, so that negative inside there stays. Again, -1 to the 3/5 would be -1 times -1 times -1. So that's -1 to the third, which would be -1. Then I take the fifth root of it is what number times itself 5 times equals -1. That would be -1. And so I get -1 plus 5/3, which turns out to be 2/3. All right, f of 0, if I plug that in, I get 0. And f of 1, if I plug that in, it's 1 minus 5/3, 1 to the 3/5 power, which is 1 minus 5/3, which is -2/3. So then I can use those points to help sketch my graph. I know at -1, I've got something that looks like 2/3. I've got 0, 0. And at +1, I've got something that looks like 1, -2/3. I know the function is increasing from -infinity to -1, and it is concave up, concave down in that region. So it's going to look something like this. Between -1 and 0, it's decreasing, but it's still concave up. So it's going to look like that. Then from 0 to 1, it's still decreasing, but it's now going to be concave up. I'm not sure I said that correctly before. From -infinity to 0, it's concave down, which is what I drew. When I go from 0 to 1, concave up, but decreasing. And then from 1 to infinity, it continues to be concave up and goes, but is an increase, and gets this image here. Notice how this is symmetric about the origin. If I take what's on the right-hand side, if I put a pin at the origin, and I just drew the right-hand side, and then I rotated it 180 degrees, I would get the image that's on the left-hand side. And so this is the answer to the sketch of the graph. Hopefully that helps. All right, thank you.